So our next topic is that of the energy balance, where we will move towards constant surface heat flux case. Uh, so let's start this energy balance. The energy balance is very simple. We have applied those energy balance on various occasions in the past. Over here we are considering a differential element. Over here on one side of this element the temperature is Tm, and on the other side it is Tm plus dTm, means change in the mean temperature of the fluid. And this has a length of dx. This differential element has a length of dx. So therefore the change in the convective heat transfer may be written as mcp delta T, where delta T would be the temperature on one side of the element minus the temperature on the other side of the element. So over here this Tm will get cancelled out and we will have dTm only. This Q can then be written in this form, because Q would be over here it is written in the form of heat flux times area. So Q double dash is the heat flux times area. Area would be the perimeter times dx. If you remember, we had done the same kind of thing while we had started the fins, the topic of fins. So perimeter would be the perimeter times dx. So that would be the area, which is also mentioned over here as well. And the right hand side remains unchanged. Then a very simple manipulation, dTm by dx. So we are bringing all the d's on one side, differential parameters on one side, and the rest on the other side. So the other side would be the heat flux times P over mcp. The heat flux times P over mcp. P is the perimeter. So P remains P and mcp remains mcp, and then we can write the heat flux as H times delta T. So therefore we can write it as H times Ts minus Tm. Then this dTm by dx, which we had written over here, dTm by dx, which is heat flux times P over mcp, is in fact not a function of x, because it is a heat flux times perimeter. So it is not really a function of x, because there is nothing which is changing with x. Now if we take this x on the other side, and if we then integrate both the left hand side and the right hand side, so integral of dTm from Tmi to some Tmx. Tmi means the mean temperature of the fluid at initial location, or it may be the point where the fluid enters the pipe. And similarly Tmx may be Tm naught, maybe not necessarily. If we write it as Tm naught, it means that we are talking about the mean or bulk temperature of the fluid at the outlet of the pipe, or it may not be at the outlet of the pipe, it may be at any intermediate section. So that is why we have written it as Tmx. Whereas on the right hand side it would simply be integral of dx, because as just said, all those things are in fact independent of x. So integrating the left hand side would give us Tm, and if we put the limits, so it would be Tmx minus Tmi, right? Upper limit minus the lower limit. So it would be Tmx minus Tmi. So if we have Tmx on this side, and if we take Tmi on the other side, so it would be written with a positive sign. And the heat flux times V over mcp times integral of x is x, and when we put the limits, it would be x minus 0 means x. So this is what we will get over here. Now what does this mean? It means that the mean temperature varies linearly with x. Mean temperature varies linearly with x, and this is what is shown over here. This is what is shown over here, that Tm in fact varies linearly with x. So the mean temperature of the fluid would vary linearly with x in the case of constant surface heat flux conditions. So therefore the mean temperature will vary linearly with x. Over here, as I was telling you earlier, that the perimeter of course would be having some constant value, mass would also be having, or mass flow would be having some constant value, and Cp of water or air or whatever it is would be having a constant value over a certain temperature range. So, and if it is constant surface heat flux condition, it means we are saying ourselves that the heat flux is constant and is not varying with x. So therefore this whole ratio will therefore be independent of x. Now over here we have seen that Tm is a linear function of x, and over here we can see that this region is the entrance region and this is then the fully developed region. So this is Tm and this is Ts. So in fact, if it is a constant surface heat flux case, then Ts will not remain constant. Of course, if the surface heat flux is constant, then Ts will change, and if Ts remains constant, then of course the heat flux will vary, as we had discussed earlier in the case of flat plate. So over here you can see that Ts increases and then increases in the entrance region if it is gaining heat from the fluid. So if T infinity is greater than Ts, then Ts would be increasing, right? Or it may be the other way around. So then when it reaches the fully developed region, this curve sort of becomes linear. Right? This curve becomes linear, and when this curve would become linear, you will notice that the difference between the two means Ts minus Tm. That the difference between the two means Ts minus Tm will become constant. It will become constant. So in the entrance region, this Ts minus Tm will vary. However, in the fully developed region under constant surface heat flux conditions, this Ts minus Tm will also become a constant quantity. Now moving forward, if this is we are still discussing the constant surface heat flux case. And it is shown that in the entrance region, this Ts has got sort of a non-linear behavior, but when it enters the fully developed region, it becomes constant. And this is the curve for Tm, which of course it is the same diagram that we were looking at on the previous page, but this diagram has been taken from Incorporate and Debit, and this one has been taken from Nusselt. Of course, these both diagrams are in fact the same diagrams, but over here it is very clearly shown that in the fully developed region, the difference between the Ts and Tm, it also becomes constant. So in fully developed flow in a tube subjected to a constant surface heat flux condition, the temperature gradient would therefore be independent of x. The temperature gradient would therefore be independent of x, and thus the shape of the temperature profile does not change along the length of the tube. So its shape would therefore become constant. However, the values of Tm and Ts would keep on changing. This is the same old discussion that we are having again. The Tm will change and Ts will also change if it is constant surface heat flux condition, but in such a manner that the shape of the temperature profile will not change. However, it will be smaller or larger at various locations. Now coming on to the constant surface temperature condition. Before we start constant surface temperature case, just one point worth mentioning over here is that Ts would be minimum at the inlet. Why Ts would be minimum at the inlet? Because it is the constant surface heat flux condition. So Q is constant, right? And H would be maximum at inlet. Remember that decline in the value of H when the flow is either all laminar or all turbulent. So therefore, if we make use of that particular equation of convection, HA times delta T, so we will write it as HA Q is equal to H times A times TS minus TM. Now since Tm is a minimum at the inlet and Q is to remain constant, right? So Q is to remain constant, and let's say Q by A or heat flux is to remain constant. So on the other side we have got three parameters, H, Ts and Tm. Now since H is maximum at the inlet, and now it is between Ts and Tm. So so therefore Ts would be a minimum, so that the product of H and Ts minus Tm may remain constant, because on the left hand side we have the surface heat flux Q by A. So if on the right hand side we have H multiplied by Ts minus Tm. So if Ts is if H is maximum at the inlet, so therefore Ts would be minimum. Now moving onwards to the constant surface temperature case. So dTm by dx. This dTm by dx can be written in this form. It is by definition. It is in fact by definition that change in this temperature may be written in form d of delta T over dx, and this may then be written as Ts minus Tm. Delta T may be written as Ts minus Tm. See, if we write this Ts minus Tm in place of delta T, right? So if we go back from here, we will get the same thing again. How? Because it would be the differential of Ts. Now if it is the constant surface temperature case, so what would be the change in Ts? Of course it would be 0, because it is the constant surface temperature case. So change in Ts would then be 0, minus and minus would become plus, and it would be dTm by dx. So we will get dTm by dx back. So we have manipulatedly written it in those steps. And this dTm by dx is heat flux times perimeter over mass flow times Cp. This is what we had written like 3 slides ago, where we had applied that energy balance. And then this heat flux may be written as H times delta T again. So we, now this so therefore this d of delta T over this delta T. So what we are doing is that we are bringing this delta T into the denominator of this d delta T, and we are taking this dx, into here. So it will go into the numerator of the right hand side. So it will become, first of all there would be a negative sign, and then we would have P over mass times Cp times H, and this delta T has already been taken into the denominator of the left hand side. So therefore dx will come over here into the numerator of the right hand side. Now if we then integrate on both sides, from if you take a look at the limits over here, the limits are delta Ti and delta T naught. Now what is delta Ti and delta T naught? Delta T at inlet, you may call it delta T at inlet, and you may call delta T naught as delta T at outlet. Delta T means temperature difference. So it is the temperature difference between Ts and Tm. It is the temperature difference between Ts and Tm at inlet. And similarly delta T naught means the temperature difference between Ts and Tm at exit, at outlet. This is what has been shown over here. in this particular diagram. See, Ts is in fact a constant quantity because we are considering the constant surface temperature case. So therefore Ts will remain constant. However, the heat flux would vary, and Tm would have its usual. Tm may increase or it may decrease, right? It may go either way. So the difference between Ts and Tm at the inlet would be delta T at inlet, and similarly the difference between Ts and mean temperature of the fluid at outlet would be delta T at outlet. The rest of the things remain the same, d of delta T over delta T, and on the right hand side we have minus P upon mCp times integral of h dx times integral of h dx. Now if we multiply and divide by L and give it this particular form, and I hope you will readily recall this particular form, that integral of h dx over L is in fact h bar, is in fact the average heat transfer coefficient which has been mentioned over here. That is why we divided and multiplied it by the length of the pipe. So on the left hand side it says integral of dx over x, d delta t over delta t. If we for the time being call delta t as x, so it is integral of dx over x. So the integral of 1 over x dx is log of x, because upon differentiating log of x we get 1 over x, so it would be log of x. And what is x over here? X is in fact delta t, or you may call it y, it doesn't make any difference. So log of delta t would be the integral on the left hand side, and when we put the those two limits over there, so it would be log of delta t naught minus log of delta ti, right? Upper value minus lower value, upper limit minus lower limit, and log a minus log b can then be written as log of a upon b. So that is why we can write it as log of delta t naught over delta ti. On the right hand side it is minus pl over mcp times hl bar. So therefore if we take the exponent on both sides, so the log we will be able to get rid of log from the left hand side. So therefore on the left hand side we will have delta t naught over delta ti, and on the right hand side it would be, the whole right hand side will be in the power of e. So it would be e to the power whatever is written over here in the on the right hand side. Now writing delta t naught as Ts minus Tm, Tm naught means mean temperature of the fluid at outlet, and delta Ti can then be written as Ts minus mean temperature of the fluid at inlet, and the right hand side remains unchanged. Or it may be written in this form, right? As I was telling you, in the case of the constant surface heat flux condition, it may not always be Tm naught, rather it may be in general form, and then we may write it as Tmx. So Tmx would be the mean temperature at any particular location, not necessarily at the exit. It may be at any particular location before the exit even. So then it would not be this L will then be written as x and not L, because whatever that x is, whatever that location is, will be put over there. Now Q convection can be written as mCp delta T, but over here it would be delta T at inlet minus delta T at outlet. We have written it in this particular form because we know that over here delta Ti is greater than delta T naught. So it would no more be Ts minus T infinity. Right? So it would be, it can be written in that form as well. See, what is delta Ti? In fact, I had told you earlier that in this case we would write Q convection as mCp times Tmi minus Tm naught, right? So over here it means the same thing. What is delta Ti? It is Ts minus Tmi, and minus delta T naught. What is Tm naught? Ts minus Tm naught. So out of these two, Ts will get cancelled out, and we will again have that thing Tmi minus Tm naught or Tm naught minus Tmi. Right? So this is the same form that we have written it, but in a different manner. So it is again m mass flow times Cp times Tmi minus Tm naught or Tm naught minus Tmi. Because the fluid is getting heated up, so it would be Tm naught minus Tmi, and this negative will make Tm naught positive. Now from this step, mass flow times Cp, all those are mass flows, right? So mass flow times Cp can be written in this form, and what is that form? Mass flow times Cp will be taken over here, so it would be minus Pl times h bar, and this left hand side will come into the denominator, so over log of delta T naught over delta Ti. So perimeter times L can then be written as area. So it is h bar times area. The denominator remains unchanged, right? And then if we multiply it with this, if we multiply and divide it in this by this particular term, we will discuss in a bit that why we have multiplied and divided it by this particular term. In fact, these two terms are these two terms, T naught and Ti, delta T naught and delta Ti. So we are multiplying and dividing it by delta T. You may write delta T naught minus delta Ti. It would not make any difference, because that again multiplying and dividing by delta Ti minus delta T naught or delta T naught minus delta Ti mean the same thing. They mean the same thing. Now mCp times this delta Ti minus delta T naught has been brought in on the left hand side of the equation, so therefore it will appear in the numerator, is equal to so mCp delta T is what? It is nothing but Q. This is written over here. This is in fact Q, heat transfer due to convection. So what are we left with on the right hand side? We are left with HA. So we have got this HA over here, or rather H bar A, times this thing has been taken over there, times delta Ti minus delta T naught over log of delta T naught minus delta Ti. Now this delta T, so this negative sign has been brought, this negative sign has been multiplied over here. So it therefore becomes delta T naught minus delta Ti. So therefore it becomes delta T naught minus delta Ti over log of delta T naught minus delta Ti. So it is delta T naught, so we have log of delta T naught, and then it is minus delta Ti, so we have minus log of delta Ti, or delta Ti written in the denominator of the log. So it is in fact HA, it is in fact a form of HA delta T. It is in fact a different form of HA delta T, where delta T is not delta T. Rather it is delta T at exit minus delta T at inlet over log of delta T at exit over delta T at inlet. This particular parameter, this particular ratio is called LMTD. LMTD means log mean temperature difference. Log mean temperature difference, and some people call it as LMTD, or some people write it in this form, delta T LM. Delta T LM means log mean temperature difference. Now what is this log mean temperature difference? See, delta T is not constant at inlet and exit. So therefore this, if we simply take delta T, so that would not give us that accurate results as this parameter would give us. So when the constant surface temperature condition is used in the case of flow through a pipe, so then we do not write it as delta T simply, rather because the change in Ts and Tm is not constant. Remember, the change in Ts and Tm was constant over there in the constant heat flux case when the flow was fully developed. But over here it is not the case. Means Ts and Tm are not, the change in Ts and Tm is not constant. Rather it is a large value at some other point, and it is having a small value at some other point. So in order to take into account this non-linearity in delta T between Ts and Tm, we do not use simply Ts minus Tm or delta T at exit minus delta T at inlet. Rather we take into account this logarithmic change in temperature, which we call log mean temperature difference. Okay. Now for laminar flow in circular tubes in the fully developed region. The Nusselt number is given as 4.36 for the constant heat flux case, and it is given as 3.66 for constant temperature case. Remember, we were discussing a few slides ago that I can show you over here. That the Nusselt number, that the value of H, and of course the Nusselt number, that the value of H would become constant in the fully developed flow. So that value is in fact, that value is found out to be, we are not going into the details and derivations, is 4.36 for the constant surface heat flux case condition, and it is 3.66 for constant temperature case or condition. Now this is the same thing that has been shown over here, that Nusselt number would become constant to a value of 3.66 for constant surface temperature case, otherwise it would continuously decrease, and once the fully developed region starts, it would be having a constant value of 3.66, and with a drop in the value of H and of course in the value of the Nusselt number in the entrance region, once the flow becomes fully developed, the value becomes 4.36. Now this is for the local value, and this is for the average Nusselt number values. In fact, they have considered two cases. One is the thermal entry length, and the other one is the combined entry length. The thermal entry length is shown with a discontinuous line, whereas the combined entry length is shown with a continuous line. And over here you can see that the thermal entry length problem means we are assuming that the thermal conditions develop in the presence of a fully developed velocity profile, right? And if we are talking about combined entry length problem, it means that the temperature and velocity profiles develop simultaneously, right? Now this is the expression for the Nusselt number, which is used in the to find out the Nusselt number in the entry region, where its value will not be a constant quantity, rather its value will change. So this is how so we will go over those expressions while we would be solving the problems. Now for the turbulent flow. For the turbulent flow, for the fully developed in both ways, hydrodynamically and as well thermally. For fully developed turbulent flow, because over here in the title it says turbulent flow in circular tubes. The local Nusselt number may be obtained from a very famous equation, which is famous by the name of Dittus-Boelter equation. So Dittus-Boelter equation has this form of 0.023 Reynolds 4/5 and Prandtl raised to the power n, where n is 0.4 for heating. For heating means Ts would be greater than Tm. So if temperature of the surface is greater than temperature of the fluid, so the fluid would be getting heated up, and if this is the case, n would be taken as 0.4 and n is taken as 0.3 if it is the opposite case for cooling of the fluid. It means that Ts is less than Tm or T infinity, but we really do not use the term T infinity because it is not free stream. So if Ts is less than Tm, so Ts is greater than if Ts is less than Tm, it means that temperature of the fluid is greater than the temperature of the surface. So the fluid will lose energy to the surface, and therefore it will be getting cooled down. So all the properties would be evaluated at Tm. Now there is another expression which is called Cedar and Tate equation. Again, these are the name of those two gentlemen who came up with this expression. Nusselt number can be evaluated in turbulent flow using this expression: 0.027 Reynolds to the power 4 by 5 Prandtl to the power 1 by 3 times mu by mu s. And in here the properties, all the properties are evaluated at Tm except mu s, which will be evaluated at Ts. So there are again various expressions, but Ditters-Boelter equation is more commonly used as compared to other expressions for turbulent flow in circular tubes. For fully developed flow, for fully developed turbulent flow. For fully developed laminar flow, it would be having the values of the 3.66 and 4.36. Now, the last thing before we start solving a few of the problems so as to get an in-depth understanding is this topic of convective correlations in non-circular tubes. Non-circular tubes means we may not always have a circular cross-sectional tube, rather we may have a square cross-section or rectangular cross-section. So it is table 8.1 of our book, and it says the Nusselt numbers and friction factors for fully developed laminar flow in tubes of differing cross sections. So we have just seen that in the case of uniform heat flux, Nusselt number would be having a value of 4.36, whereas the Nusselt number would be having a value of 3.66 if it is a constant temperature case. Now, however, those values will only stand or will only hold good if the cross section is circular. But if the cross section is not circular, then the different values of Nusselt number would be chosen from this table depending upon whether the case is that of constant heat flux or constant temperature. And over here we are given the dimensions A and B, and we are also given the ratio of those dimensions. So we will pick up the corresponding values of Nusselt number depending upon the ratio of the dimensions, and depending upon whether it is constant heat flux case or constant surface temperature case. Over here we must discuss a very important concept regarding which is called hydraulic diameter. Now, hydraulic diameter is given as this thing, 4 times cross sectional area over wetted perimeter. This is called wetted perimeter. So hydraulic diameter concept is used in several cases. For example, in non-circular cross sections as well. We need to discuss hydraulic diameter in a bit of detail. So in fact, if we use this basic expression which is written over here for hydraulic diameter, which is 4 times cross sectional area over perimeter, and if we work it out for example a circular pipe, so it would come out to be D. See, it would be 4 times cross sectional area. Cross sectional area would be pi by 4 D square. So 4 will get cancelled out, and we would be having pi D square, and the perimeter of a circular pipe is pi D. So pi D square upon pi D would be D. So of course the hydraulic diameter of a circular pipe would be D, but for other geometries apart from circular cross sections, so what it does is that it provides an equivalent, you may say that it provides an equivalent diameter equivalent to the circular ones, if the geometry that we have in hand is non-circular. So So this is how the hydraulic diameter is used, and this is what it is used for. So whatever geometry we are given, for example, if we are given this particular geometry, let's say this one, A and B. So cross section area would be A times B, and perimeter would be A plus B plus A plus B, means 2A plus B. So whatever is the geometry, we can put the cross section area over there and the perimeter over there to find out the hydraulic diameter. It is also called wetted perimeter. Wetted perimeter means WETTED, wetted. So if the flow is not taking place completely through a pipe, so we need to only put that perimeter for which that fluid is in contact with the pipe. So that is why it is called wetted perimeter. So let's start now solving few questions.